Good evening, everybody. So yesterday we completed our discussion with respect to decision trees. Now we will be doing random forest next. So if you guys are having any doubts with respect to decision trees, you can ask me in the chat section here. Okay, so now here if you see, we're basically having two different data points, right? So we have two different, we have the same graph, but we have two different decision trees that is created from the exact same data set, right? So basically what we're trying to understand is that it's not necessary that for a given data set, the splits that we will do will be the same and that we'll get the same output, right? It is not a default thing, okay? So because the same data set can lead to different decision trees, okay? And that might even classify the samples differently as well, right? So essentially the idea behind random forest is that we have multiple decision trees and we take the combined opinion of all of these decision trees to take our decision, okay? So let's say that you go to the doctor and he suggests some procedure for the illness that you're having, right? In most scenarios, you don't actually just, uh, listen to what they say and immediately just do that, right? Most of the times, you always take a second opinion, or if you are not convinced even then you'll take more opinions, right? So you basically trust that one doctor is having good amount of knowledge, another doctor is also having good amount of knowledge, right? It's not that you're doubting their knowledge. You're just seeing if there is something that one doctor might have missed out, if another doctor can find, right? So in that way, if multiple people who are all knowledgeable are giving you the same opinion, then that's the best thing that you're supposed to do, right? So this is how we think about in a particular scenario. Similarly, that's what we do even in case of decision tree and random forest. So random forest is, let's say I have 500 different decision trees. So I have trained 500 decision trees. Now for um, each prediction that I'm supposed to do, or I make a prediction from all the 500 decision trees. Okay, all these decision trees are trained on the exact same data, but they've done splits differently and they've classified points differently, all of that, okay? And they've been pruned to different extent. So all of them will, each decision tree will give a classification of its own, and then in all of those you finally conclude by taking the consolidated opinion, and then the final thing, whatever is having majority, that is what you pick as your decision, right? So the idea is that if one decision tree has not picked up or learned a particular type of a pattern, some other decision tree might have done that, right? So that is how it works. So you take combined opinions of all of them and then base your final decision based on that, okay? So this is how our random forest algorithm works. If you guys are having any doubts regarding what we've discussed so far, you can ask in the chat section. Okay, so I'm assuming that there are no doubts. So what we'll do is let's complete the pre-processing with the same social network ads CSV file itself. Please do the pre-processing in a new notebook and put a message in the chat once you're ready, so that then we will move ahead and implement random forest. Okay, so then we'll continue the steps after that. So for working with random forest, we need to import the ensemble library, wherein we'll import the random forest classifier. Okay, so we'll create an object of this. I'm going to call it CLA itself, random forest classifier. And here in the parameters, we need to pass basically what are the number of estimators, that is how many decision trees you want to actually change. So by default, the value is 100. So basically it's going to take for 100 decision trees on the same data set, and then it's going to take a combined decision finally. Okay, so I'm not going to change the default value. Okay, now once that is done, I'll just use the fit function on X train and Y train. Then finally we can do the prediction, right? So we can do CLA dot predict, and here we can pass I just have to pass X test, correct? Yeah. So I just have to pass X test, and this will give me the pred. So I'll just print pred here. So it's going to be all of these outputs. Okay. So quickly implement these code cells and let me know once you're done in the chat. Okay, so I'm assuming that you guys have done it. So now we can find out what is the accuracy score, and we can also see the confusion matrix. So from sklearn.metrics, so we've got an accuracy of 85%, which is higher than what we had got for our random forest. For most cases, we will get a higher value itself because we're taking the best of all the scenarios. It will mostly give us a better value. So here we can see that there are 11 and 4. So these are our false negatives and positives, right? So, and then finally, another thing that we can do is plot the graph. So I'll just quickly, from the decision tree itself, I'll just copy this, and we can plot the graph and see how our model looks. Okay, so this is random forest. Other than that, I don't have any other changes to make. Okay, I always miss doing this. Let's just import it here itself. So this should give us the graph output, and then we'll be able to visualize. So this graph will look very similar to how the graph of decision tree looked, except that here it'll be, there it was like more finer fixed straight lines. This will have a lot more splits because it's an average of all of them. So basically, if you interpolate all of these graphs on each other, the combined value together is what forms it. So the graph will also look like multiple graphs being superimposed on each other. So please execute these code cells. We'll look into the graph. Again, this graph is also a non-linear graph itself, right? So this was the graph we had got in case of decision tree. And this is what we've got in case of random forest, right? And you can see the graphs are much different. And it is a they have basically put on top of each other and got this graph, okay? So I think this will complete our discussion with respect to random forest classification. If you guys are having any doubts regarding what we have discussed so far, or any of the classification topics, you can ask me in the chat. And once you're done, you can put a message done with the accuracy score that you have got for random forest. And then we will proceed to support vector machines. All of you, please drop in the accuracy score that you have got for random forest. So now that we've understood the basics of support vector machines, right, we already saw how support vector machines are different from the other classification examples, right? We also saw how it is different from the logistic regression or the linear regression. So basically linear regression and support vector machines, both of them are with, basically trying to find a line of separator or a line that fits the data points. So we saw how they're different, right? So any doubts regarding what we've discussed so far? Shall we move ahead with non-linear SVM? Any doubts regarding this? Please put in a message in the chat, yes or no, whether or not you have any doubts. Okay, so no doubts. Awesome. So now we'll move ahead with non-linear SVM then, right? So in the previous slide, we saw how we had this separator and there was a proper linear separator that we had between them. Now that may not be the scenario in all the situations, right? So let's start with the one-dimensional plane, right? So with the one-dimensional axis. Now, if I had to find a linear separator, in case of 1D plane, it's going to be a point. Basically, and I need to find out which point before I can classify to one sample and what after it, right? So I can't really take a decision like that for this place, right? Because any point I take will not serve justice to all the points, right? So if I take a point here and say everything to the right of it is red and everything to the left of it is green, then 3 points will be misclassified. Again, if I do the same thing here and then I decide everything to the left is red and everything to the right is green, again 3 points will be misclassified. So there is no real way in which we can actually do this in a there's no linear separator that we can have between them. Okay, now to address this issue, there are two different ways we can go about with this. Okay, so one is that we increase the dimension of the data itself. That is one way to go about it. So we increase its dimension. So we add a y-axis component to it, or do basically some set of mathematical functions and add a value to it into it. And the other would be to use the kernel trick. So we'll discuss both of these and what is the drawback of each of them as well, right? So the initial idea is to increase the dimension and basically plot these points in a new dimension, and that should be able to, and in the new dimension we should have a linear separator between them. Okay, so basically if I move all these points, I'll subtract a constant value from all of them, move all of them a little more this side. Okay, and then I find the square of that. So here you can see finding the square actually increases its dimension, right? And then we plot these points basically on the graph. Now, by doing that, what happens is once these points are basically plotted on that particular graph, this is the new data space that we're getting. And here we're having a linear separator that separates the 2 points. Now, when we do something like this, what exactly happens is that I have perfectly found the separator between the two, but every single data point I've increased another dimension. So we have a lot of mathematical calculation to be done. For a very small data set, this might seem reasonable thing to do, but it doesn't really help because, in the end, you're basically doing a lot of processing and this is just, very computationally expensive, right? So we don't want to do this. So, I mean, that's how we can get a linear separator. Now, for any scenario, if we have a 2D graph, then we can increase it to a 3D place. And in the 3D plane, we'll be able to have a separator. So this is also a 2D graph, right? So in the beginning, we started with a one-dimensional thing. We changed it to two-dimensional and found a separator. Similarly, a two-dimensional thing, we would change it to a 3D space and find a plane that separates the two. So there has to be some set of mathematical operation that we should find that should be able to do this. For all the data sets, you can definitely do it, but the entire task of finding the right mathematical operation that will increase the dimension is difficult, and also that it's a very computationally expensive thing to do. So any doubts regarding what we've discussed so far? I hope it's clear to you guys still here. Next, we'll start off with the kernel method of how we can do it. Any doubts? Okay, so now we'll start off with the RBF kernel, okay? So the kernel is basically given by this particular equation. So this here, e to the power minus x minus L divided by 2 sigma squared. So this is what the kernel function stands for. It is a function of the locus and the diff point itself, okay? So the locus is actually even to the center where this entire function reaches its peak, which is actually at 0. And x is any point that you take on the xy plane, okay? So basically, if I pick any single point in this entire plot, that will correspond to x, okay? And now let's break this equation into smaller parts so that it's okay. So can you let me know from where it wasn't audible, or I can continue from where, continue from this graph? What part did you guys hear last? Okay, so basically here we saw about how that particular graph can, how we can actually use the kernel functions to do this, right? So now there's no requirement for us to change or increase the dimension in our data set. We can directly just use the formula. But usually our data set would not be as simple as that we see here or here, right? So our data set is usually just not one spherical that actually differentiates. So our data set could look something like this for all you know, right? So if you had to, get a separator that looks something like this, it wouldn't be possible for us to do it easily with any of the ways that easily to just use a single kernel function to do that. So then in that scenario, what we do is we use multiple kernel functions with different locuses, right? And all of them are having a different standard deviation because of which its peak and its the peak as well as the spread that it has is going to be different, right? So that will cater to us getting a lot of these, a curve that looks something like this, right? So we can manage and basically have any type of sample, like any type of data set can be used using the kernel function. So we just saw the Gaussian, the RBF kernel. We also have a lot other kernels which are basically built on another different mathematical formula, right? So we also have a polynomial kernel function. We have a sigmoid kernel function. So we have various functions like that, like others as well, right? So if you guys are having any doubts with respect to support vector machines, then you can put it in the chat. And if you're not having any doubts with respect to support vector machine, then we will start off with the implementation with the normal kernel and as well as with the RBF kernel. Okay, so we'll work with the linear kernel, the RBF kernel. We'll try all of the different kernels and see the different graphs that we get on the same data set, right? So any doubts regarding support vector machines? Any doubts, guys, in support vector machines? I did not get any response. Doubts, yes or no? If you're having a doubt, then you please ask. If you're not having any doubts, then please put a message no in the group chat. Okay, so if you're not having any doubts, then you can open a new notebook and import the same CSV file, do the pre-processing, and put a message in the chat once you're done with the pre-processing. Is the pre-processing done? Okay, so we'll continue with the implementation of support vector machine, which is the last final algorithm that we're learning. So we'll do that tomorrow, followed by something called, let's compare all of the different classification algorithms together for the same data set. So we'll have one comparing classification assignment that we will have tomorrow. So we will finish both of this tomorrow, and then we can start off with our introduction to neural networks, followed by the projects that you will have to complete in a matter of 10 days, 5 days for one project. So we will do that starting from um, basically this week will complete this syllabus. Okay. So if you guys are having any doubts, you can ask me in the chat. Otherwise, we can wrap up today's class. Tomorrow, we will implement our one last final classification algorithm, which is support vector machines. Okay. Thank you, everybody, for attending.